Welcome to section 2.8 on related rates. So in a related rates problem, we want to compute the rate of change of one quantity in terms of the rate of change of another quantity. The procedure is to find an equation relating these two quantities and then use the chain rule to differentiate both sides with respect to time. So, example 1. I have air is pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. We want to know how fast is the radius of the balloon increasing when the diameter is 50 centimeters. So the formula we need to use is the volume is equal to 4/3 times pi r cubed. And because of the diameter being 50 centimeters, the radius we're going to be using for this is 25, so half of that. We could differentiate now this volume formula. This is the derivative of v with respect to t. That is going to be the derivative of the volume with respect to the rate times the derivative of the rate with respect to time, right? And we were told in the problem about how the volume increases at a rate of that 100 centimeters per second, and we want to find about how fast the radius is increasing. So we have our parts based on this. From our formula up here, we have the derivative of v with respect to r. So this equation is going to be 4 times pi times r squared times the derivative of r with respect to t. And this is supposed to be equal to 100. So solving for, we could put the 25 in for the radius in this before we go about solving it. So 100 is equal to 4 times pi times 25 squared times the derivative of r with respect to t. We could divide by 4 pi times 25 squared and get the derivative of r with respect to t is whatever we get when we do 100 divided by 4 times pi times 25 squared, which would give us 1/25 pi. And that rounds to be about 0.0127 centimeters per second. For my second example, each side of a square is increasing at a rate of 2 centimeters per second. At what rate in centimeters squared per second is the area of the square increasing when the area of the square is 81 centimeters squared? So since this is a square, this is just a is equal to s squared as our formula. We know that the area that we want for this is 81. That's the information there that we got. Based on our formula, that means s, each side length had to be 9 centimeters for that to make sense. So the formula that we would use is the derivative of the area with respect to time is the derivative of the area with respect to the side length times the derivative of the side length with respect to time. So this is equal to the derivative of s squared, which is 2s, times ds over dt. So the side length here is 9. We have 2 times 9, and we were told that the side length is increasing by 2 centimeters per second. So we multiply this by 2. So 2 times 9 times 2, this gives us 36 centimeters squared per second. And that's the derivative of the area with respect to time. For example 3, the length of a rectangle is increasing at a rate of 3 centimeters per second, and its width is increasing at a rate of 9 centimeters per second. We want when the length is 9 centimeters and the width is 4 centimeters, how fast is the area of the rectangle increasing in centimeters squared per second? So this formula is the length times the width, since it's just a rectangle. So the derivative of this area with respect to time uses the product rule for this. We take the length times the derivative of the width with respect to time, plus the width times the derivative of the length with respect to time. So we got the length of 9 centimeters times the derivative of the width with respect to time was given by 9 centimeters, plus the width, which was 4, times the derivative of the length with respect to time, which is 3. So 81 plus 12, we would get 93 centimeters squared per second. Example 4. A cylindrical tank with radius 3 meters is being filled with water at a rate of 4 cubic meters per minute. We want to know how fast is the height of the water increasing in meters per minute. This formula is pi times r squared times h. And using a radius of 3, this volume becomes pi times 3 squared times h. So 9 pi h. So the derivative of v with respect to t, this is going to be the derivative of v with respect to the height times the derivative of the height with respect to t. So, for us to solve this, this will be the derivative of v with respect to h. That would be taking the derivative of this 9 pi h with respect to h. So that'd just be 9 pi times the derivative of h with respect to t. And we were told that the rate of the volume increasing with respect to time is 4. So we have 4 is equal to 9 times pi times dh over dt. So the derivative of the height with respect to t, this would be 4 divided by 9 pi. And this is, again, in meters per minute. And then finally, example 5. The radius of a sphere is increasing at a rate of 2 millimeters per second. How fast is the volume increasing in cubic millimeters per second when the diameter is 100 millimeters? So this volume formula will be 4/3 times pi r cubed. So this is the derivative of the volume with respect to time, is the derivative of the volume with respect to the radius, times the derivative of the radius with respect to time. So the derivative of the volume with respect to the radius is 4/3 times pi times 3 r squared times the derivative of r with respect to t. So 4 times pi times 1/2 of 100, since the 100 is the diameter, squared times 2. This would give us 20,000 pi in cubic millimeters per second. Let me know if you have any questions or concerns. Thank you.